So for those who in the first project, it was exploratory data analysis. We're going to be using the same data set that they were using. So just to bring everyone up to speed, for those that didn't attend, we're looking at collisions that happened in Washington State from the year essentially 2004 into, I think, 2019, possibly in 2020. These are just some of the exploratory data statistics that came out of the exploratory data analysis project, pretty high level. And today I'm hoping that we can sort of pull you through some time series components that you're looking for when you're looking at traditional time series data sets. Differentiate between univariate and multivariate forecasting methods. I'm not sure that we're going to get into the multivariate forecasting methods today. And then also develop a forecast model to predict future collisions. Give me just a sec, I'm getting pinged. Okay. Awesome. So time series forecasting or time series analysis is usually you're looking at one variable. In this case, for collisions data set, you could look at number of fatalities, you could look at the number of collisions, and then you can granularize that data, so daily, weekly, monthly, and you end up trying to predict some number of periods into the future. Here, we're working on also showing you that the time series that you use and the analysis that you do changes based on sort of the granularity that you use as well. What I say a lot of times when I work with this is I'm just trying to pull out some sort of like the primary components of the data. The analogy that I usually use is if I were to have a crystal ball and data science is that crystal ball, I'm just trying to remove as much of that sort of like gray cloudiness out of my crystal ball. But at the end of the day, we're really just using future prediction from historical events, which is why you'll see like a lot of stock prices predictions didn't respond correctly to a global pandemic. It was something that they hadn't been trained on. Okay. So today I'm going to go through some of the primary components of time series analysis. So when you're looking at time series observations, a lot of times you break down the observations into having sort of 4 primary components. So that's trend, seasonality, or cyclicality, and then residuals. So those are sort of like any irregularities that don't fall into those other 3. If you are an engineer, maybe to begin with, you didn't come from like a traditional time series like statistics and business analysis background, this is analogous or very closely analogous to a Fourier transform on a signal over time, and then you pull out your top 3 components there. So for me, that was what made it click. I hope that hopefully something will help you click too. So we're going to go ahead and start off and import some packages. Go ahead and restart and clear everything. And Erin, should I be asking if like everyone's okay? Should I take any breaks here? My first time doing this.
It's totally up to you. Poll if you want to poll folks. Otherwise, Erica and myself and Niwaka will all keep an eye on the chat window. If somebody has a question, feel free to type it in, and we'll try to get to it when we can.
Okay, awesome. Yeah, I can hear the questions, so I'll flip back over if I hear those going off. And also, don't please feel free to interrupt me here if you have a question or if I've done something that doesn't vibe. Just let me know. And then if we like run into a place where maybe there's too many questions or something like that, then we'll take it as it comes. Okay. So I'm just going to read the data frame straight from the URL that was provided. this might take a little bit, especially with all of us pulling it at the same time. I'm just going to copy that over so that if I make any changes to the data, I can easily go back and just recopy. I don't have to re-pull from that URL. Awesome. All right, so now I'm just going to do a few checks, make sure we're not missing any data, pull out some overall trends in the data. I'm also going to aggregate the injuries, serious injuries, the number of people involved, fatalities, number of vehicles, things of that nature. Just trying to get an understanding of, on a daily basis, how is the data behaving. Okay, and then if we were to change that granularity to monthly, how do those change over time for fatalities, serious injuries, and minor injuries? I don't know about you guys, but this wasn't what I was expecting. Offset, like, right at the very beginning, my whole thought was I shouldn't see anything but increasing fatalities, increasing collisions, because the population is increasing and sort of the urban sprawl in Seattle is increasing. I mean, I only moved here, or came here for the first time in 2017, and then I was away for a year and came back, and just in that time, it was crazy how much growth had happened. So this sort of, it raised my alarm a little bit of like, okay, is something wrong? But there hasn't been any changes to what is reported and what isn't reported. So. Yeah. Okay. Now if we take a look at your total collisions versus your total injuries month over month, you know, just sort of again trying to get an understanding of how your data is behaving. I did think it made sense though in 2020 for us to have a drop off from more recently. There have been so few people on the roads. So. Can you guys tell me, like, if this was your analysis, just off of sort of what we were looking at as the variables that we would consider predicting, are there any of them that stand out to you more than maybe like the number of collisions or the number of incidents? Is there anything that you would have rather investigated? Why is there a dip in 2017? I'm not sure why there's a dip in 2017. Are we talking about this one here? Okay. Yeah, I'm not sure the number of people that are involved there. I don't know, Aaron or Nawaka, was that investigated in the exploratory analysis at all?
So we didn't look at these particular values in the earlier workshop, but the nice thing about looking at overall plots initially is it gives you a chance to look for suspicious outliers. In this particular case, I do not know the answer, but it certainly is worth further investigation if you're engaged in this project, right? Is there a good reason for that? Another thing that I thought was kind of interesting when I was looking at this is there was a recession end of 2006, 2007, 2008, in that time period there. But if you look at and so I mean, I would have assumed people were driving less because they had less money, people were losing their jobs. But there wasn't, at least as far as I could tell, a dramatic decrease in the number of collisions in that time period. In fact, in that time period, if you look at the total number of injuries, there's a spike around that time period. So maybe that means regardless of the fact that people don't have a lot of disposable income, maybe they're drowning their sorrows, if you will, and still engaging in questionable driving behavior.
And if we wanted to take a look at how this changes daily, we have the timestamps. So over the course of a day, hour of a day, how do these peak? So I thought that this sort of made sense. Like you see the 2 rush hours. You see the like drunk driving hours, I think is when most of the like intoxication related accidents happen. Do we know if there's been a way to how the data is collected over time? I don't understand that question there.
Sorry, I wasn't 100% sure what you said. Data collection over time?
Yeah, the last question in the chat, do we know if there has been a way to how the data is collected over time?
A change, yeah. So we're definitely going to be looking into that. It was not clear from the description in the data set that we got that there was a change in how things were being reported or recorded. But there's no doubt that over this long of a time period, changes were made, right? Databases were changed. It's inevitable. So there could definitely be some questionable recording. That's also something, obviously, you have to keep in mind at this kind of early stage.
Awesome. And then if we restrict just to, you know, sort of like the normal working hours, what does that look like? And is there a change day to day? I would hope that Saturday and Sunday, so these 2 red and green lines would be different, and they are. Awesome. Okay. So after I think we do the sort of this, just sort of get a feel on the data. If I was working for the Department of Transportation and they were asking, hey, can you guys just sort of put together a forecast on the number of accidents that are happening daily, the number of incidents, I would probably present these as a like just a level set of the assumptions that you're probably making about the data are being met, and try to build trust, I think, prior to jumping into the analysis. I don't know about you guys, but one of the things that comes back over and over again, especially in IoT data, is we can't trust your analysis because we found this one thing that didn't make sense in the data. So I oftentimes try to like build trust in the very beginning in the data, and then like what we're deciding to look on. And if I find things that don't make sense, I'll say like, okay, well, we decided to choose a threshold of you know, outside of 3 of the interquartile range so that we could work more along the normal operating behavior or something along those lines. And in this case, with this dip in 2017, I actually wasn't looking at people, the number of people involved. My target variable was just the number of incidents. So I'm glad that that was brought up. Awesome. Okay. Let's go ahead and get started then, this next part. So I go ahead and aggregate the data on a daily basis, and I'm looking at the incident date. And I'm trying to get the sum of the incidents over time. And from this, I decide that I only want to look at 2004 and up data, just because this gap at the end of 2003 didn't make sense to me. Can you guys see my screen?
Yes.
Okay, cool. So I suggested that we begin our data set at January 2004. In the past, when I've looked at data, if there's some sort of cyclical trend that I know just from a business understanding of the problem I'm trying to solve, I will oftentimes sort of like move the data one way or the other. For example, if I worked in the construction industry heavily, 2007, 2008 were big hits to the construction industry. If those years already had data anomalies that were due to like bad reporting, right? So like if the person who was in charge of pulling construction permits and counting construction permits was let go and like that data reporting no longer happened, I would probably decide we're going to start in 2009 when it picked back up or something along those lines. So understanding how to handle those strange pieces of the data, I think, is up to the beholder. So this is still 2018 because I was testing, so let's pull this back to 2004. Okay. So right off the bat, in the very beginning, I mentioned the sort of like four principal components, that's not the right way to say that, the four pieces of time series observations that I'm most interested in, that most people are most interested in. And those are your trends, again, your seasonality, your cyclicality, and then your irregular piece. So I'm going to use a seasonal decomposition here to sort of pull out what those are. And here your x-axis is like the number of periods, and then your y-axis is your target variable. So this is the account of the incident. And what I'm really looking at is seasonality. Are my residuals white noise, I think is what it's called. Like, you're looking to make sure that there's no constant variance or mean or any sort of statistical pattern that wasn't picked up in your other plots. Right, so if this had a very pronounced like cyclical pattern or seasonal pattern, then I would say that there was something that is another order that we should look into. And you can do tests for essentially randomness in your residuals as well. You wanted to test for that. One of the things also I thought was important here is just a look at the trend. So like the trend doesn't seem flat, right? So it does. You're looking to see, is there a constant up or is there a constant down over time? But this one is both. You have increasing and decreasing trend over time, which is somewhat, I wasn't expecting that. I usually say like the trend sort of can pick up on what your eyes are already seeing and what you would expect, right? So in the beginning I said that I would expect trend to be increasing over time. I would expect as you had more users, so more vehicle drivers over time, you would see an increase in the number of incidents. That just seems like a natural thing. You've got more people driving, more cars on the road, you would have more accidents. But here we're not seeing that overall direction in the data over time. And this leads to sort of one of the basics of time series forecasting, which is understanding whether or not your data is stationary. So stationary is essentially just saying, is there a time-dependent factor in your data with respect to the mean, the variance, covariance, really a lot of those like basic descriptive statistics, that they can be linked to having a relationship over time that moves up or down over time, then it's not a stationary data set. Right, so like you'll see a lot of analyses performed on stock trading, like stock prices, that'll use AutoArima, and they don't test for stationary if the data set is stationary over time, and that violates one of the first principles of using a lot of the like ARIMA are those automatic forecasting univariate methods. So one of the tests to determine if your data is stationary is to use an augmented Dickey-Fuller test. So these are two statisticians that designed a test to see if the time series has a unit root. So a unit root indicates whether or not the time series is stationary. And as I just described, stationary time series means that you aren't having dependencies on time in your data set. Here, your null hypothesis is that your time series is non-stationary, and for us to not have to take any sort of differencing or any sort of transformations to our time series, we want to reject the null hypothesis. So your ADF test statistic is actually, it should be a negative number, and then the more negative your value is, the stronger the rejection of the null hypothesis. So we'll actually test it if you use the significance levels here. And what we're sort of hoping for is that this value will be much less than these values. And that this, if you're working at that sort of 5% p-value, you also want this value to be less than it. I actually tried this both ways. I also tried using the log of the time series and doing it again to see if there would be a difference, and there was. So. Here what I'm seeing is that it's sort of stationary. I would probably not reject my null hypothesis if we're sitting in this range between a critical value of 5 and 10%. But that's, again, up to you and how confident you are. The next step that I would take is actually going to be understanding if there's an autocorrelation or a partial autocorrelation and what the effect of differencing is on the data. So does this make sense right here, what we're doing? I feel like I'm just moving really quickly and nobody's like raising their hand to stop me. There are other tests you can use also, but I think the augmented Dickey-Fuller test is the one that I see used most often. Okay. Thank you, Pat. So one of the big pieces in time series is usually autocorrelation. So autocorrelation is also known as serial correlation, and it means that there's a high correlation between your current observation and the observations in the past, which would make sense, right? That seems like, for example, if your population is growing over time, then you would expect to see a autocorrelation in your observations for every year or every 18 years. Those are to be expected. And when you plot your autocorrelation and partial autocorrelation, you should see something along those lines. So what you're looking for here is essentially as close as you can get to 0 as possible, and then your x-axis is your number of lags. So they test the lags at each one of these, or they test the correlation, excuse me, at each one of the lags. So here it looks like the best predictor of my current value is going to be my previous value and the value before that, so 2 lags. Another way to do this is actually to take your lagged values and you can run a regression using those to see what their predictive power is on your current observation and how close you get to your current observation just using your past observations. So partial autocorrelation tries to take out the linear relationship, the time dependency linearly, and rerun the correlations. What you're hoping to see in both of these plots is that there isn't correlation and there isn't partial correlations over time. But for both of these, we're seeing that there's a lag of 1 has a pretty significant predictive power on your current observation. Could anyone what are your thoughts seeing this? Like, if you see that 1 to 2 day lag is the biggest indicator, but then you also have sort of this up and down pattern, like, what are your thoughts? Yeah, definitely there's some sort of cyclical, yeah, Jackie hit the nail on the head. You've got about a 7-day cyclicality there, right? So every 7 periods is another spike. That's what I was trying to get at there. Probably didn't lead you down with the right breadcrumbs. Yeah, Rebecca, you got it too, thanks. And Shivani, I think that you're hitting the nail on the head here, right? Is like, we're trying, is there a method here for these lags that would better predict, right? There's something, an underlying structure here that we should have seen if we come back up to our seasonality or cyclicality that it looks like we also did see a little bit of. Awesome. So with me, my first thing is, okay, we should go ahead and difference on the first lag, right? Like, if we're not really stationary to something I'm comfortable with, and I'm looking for a stationary time series so that I could do sort of the simpler univariate methods like AutoArena, I'm going to go ahead and take a shift in the data. I'm going to lag the data just 1 period here, just 1 day. This is going to create a null value at your very first observation, because it's n -1 at 0, essentially. And I'm going to replot the ACF and the partial autocorrelation. And this was sort of funny because I was expecting it like, oh yes, there's still a lag, which makes sense because after your first lag, your highest indicator was a lag of 2. But we could do this in this case if I wanted to do both of them. We could try that as well. So it's really like you can try to transform and try the difference, but at the end of the day, like Wednesday is always going to be better predicted by the number of cars that were on the street on Monday. So based on the granularity here that we're using, which is just 1 day, I'm pretty sure you'll continue to see this. And it also comes back to this lagged pattern here that we saw previously. But even knowing this, I just want to see if we could run that augmented Dickey-Fuller test again. Sure, Jackie. So the difference between autocorrelation and partial autocorrelation is autocorrelation takes your value currently in, and then it looks at a lag of 1 or n -1, and it asks what's the correlation between your n and your n -1. How similar are those two? Partial autocorrelation tries to take out the linear effect over time. So it tries to take out, if you have a trend, it tries to remove that linear relationship between the data points as time progresses and rerun the correlations between the lag data sets. Okay. So I'm going to I'm going to run my augmented Dickey-Fuller test again, just to see if taking a difference of 1 had an effect on the stationary property of the data. It looks like it did, which makes me super happy. So now I can safely say that my lagged data set with a lag of 1 is stationary. Yeah, so it's the 2 values again that I'm looking at here is my statistic, my Dickey-Fuller statistic, much less than my critical values, or really less at all than my critical values. And then the other way to look at it is my p-value less than my, how do I get this up, confidence, 5%? Everyone in the room is like, she's not a statistician. So now I'm going to move into doing an ARIMA model. ARIMA stands for an autoregressive. So with autoregressive, think of lagging your data. Integrated moving average. So you're moving in 2 directions, right? Your moving average is how your average is changing forward. Autoregressive is looking in the back. So you have 3 sort of variables that you can use to try to create a model moving forward. The first one is P. This is your autoregressive component. It's the number of lags that you're going to use as predictors. So just off of what you've seen off of our autocorrelation and partial autocorrelation, what would you choose as a value of P? Seven. Why would we choose 7? It is a 7-day cycle, but that's saying that I think that Monday or Wednesday this week is going to be best. I guess that makes sense. Wednesday this week would be best predicted by Wednesday of last week. Okay, but then we know from the partial autocorrelations and autocorrelations that the biggest indicator is a lag of 1. So I would probably choose a P of 1, right? So how far in the past am I looking? And then how much differencing do you want to apply to the time series to make it stationary, right? So we just attempted this with a lag of 1 and a differencing of 1. But then we found that we still had a high autocorrelation, even doing a lag of 1 and a lag of 2 differencing. And then Q is your associated moving average portion of the model. So how are you taking your lagged forecast errors? How are your errors changing over time? There's also the ability to add a seasonal component to this. So if we lived in a state where it didn't rain like all year, if you had like a hurricane season or a monsoon season, and you were still looking at traffic data, there is the ability there for you to also add seasonal items using ARIMA. So I really like AutoARIMA because it takes all of these values, P, D, and Q, and you can go ahead and initiate them if you think that they belong at a certain place. But it's really just doing the modeling for you and then comparing your AIC for each of those models. So let's go ahead and import the library. Let's do our AutoARIMA here. So here I said I want to start at a lag of 1, like how far in the past do I want to look at? Same way with, do I want a difference on that lag? What's my max moving average number of observations? here we said seasonal is false. We could, the seasonality, there is a seasonality. We could change this to true. But then I believe it does a test for stationary, whether or not the data is stationary. So I'm going to try that. Yeah. I don't believe that the error reporting for the package is correct because we've tested for stationary on the data set that we're looking at using an augmented Dickey-Fuller test. One of the things to be wary of, though, is that your augmented Dickey-Fuller tests, they are known at producing higher than usual type 1 error. Usually, though, with this understanding here and not seeing a lot of pattern in the residual plot, it would make me believe that we are working with a stationary data set. So then we're just going to compare our AICs for each of these ARIMA models. Can someone tell me how we pick the best model here, how we pick what we would want to use? Okay, so with our AIC, which is the information criterion, I can't pronounce the first one, like the ATIME information criteria. The smaller the better. So you wouldn't compare an AIC like data set to data set, but you will compare an AIC model to model on the same data set. And it's a unitless value. So it says that the best performing model is on P of 0, a D of 1, and a Q of 3. So back to what this is meaning is it's saying don't take autoregressive component. Differentiate or take the difference between your current observation and a lag of 1. And then it looks like your moving average piece for the number of lagged forecast errors that we're looking at is around 3, which I think makes sense as far as the 3 is concerned, because that's about half a week. So you'll see your residuals change the most between the weekend and the work week. And then this, I think you guys are probably going to run into the same issue that we did, or maybe not, before. Okay, it worked this time. I couldn't get this to work earlier. I'm very happy right now. Oh no. Maybe I did something wrong here.
You have to change the here in number of periods. You can put length of Y train.
Thank you. Was there a second place that needed to happen? I think that this is the number of periods you want to move forward in your prediction. I don't think you can go greater than your test, so maybe that was a piece of it, or greater than your train. So we're probably just going to look at like the next 30 days. Did I do this wrong? Okay, sorry. This is definitely my fault here. We've already decided the number of periods we want to move forward just on Y test. So we're predicting on Y test, yes. Now let's go ahead and compare the prediction to our actuals. Compare for the year. Let's see. Sorry guys, I'm debugging on the fly here. This was a merge change from earlier that I hadn't tested.
I use greater than 2019.
Let's change. Oh, sorry. Okay, so we're looking at the data in our test between 2018 to 2019, so just for the year 2018. Yeah, so this is January to December. But AutoArima, if we just look at what our prediction was, our prediction's a little underwhelming. Right, so our prediction is saying pretty much just like it's going to be somewhere between 38 and 39 for the next year, day over day. So ARIMA is right off the bat missing the seasonality, cyclicality, even sort of like the day over day change that you would see here. Okay. So AutoArima is a pretty simple first pass. I do it to say I tried a univariate method and did a lot of the basic tests that one entrenched in time series would look for. So is your data stationary? Is there a seasonal component? What's your trend over time? Yeah. So if it's okay with you guys, I'm going to stop sharing and make a few changes, which I don't think we're supposed to do.
Well, this would be a good time for everyone to, go get something to drink. Take a 5-minute break. How about that?
That sounds good.
You can also prepare questions you have for Victoria.
Yes, we will plan to resume at 7.
Hey, Erin. Erica?
Yes.
I've made some changes to the notebook. Is it okay if we work over them in here, or should I I don't want to recommit because then everyone have to re-download, but I just did like another few changes, or I can put the code in the chat.
You can absolutely just walk through, run the code here and then let everybody know they can download the latest after. Is that what you're asking?
Yeah.
Or do you want to make it available to everybody now?
I don't know. What do you think would be better? I think if I put the code in the chat, does that seem like something we'd be okay with?
That's totally cool. Is it long, I guess?
Some of them are here. Can you still see my screen?
Yeah, no, that works great.
Oh, you can still see my screen? Okay. Yeah, so I'm just going to share using a different model.
Also, if you push your changes, people can re-download it if they want, but
Okay.
but no worries. We have definitely copied code into the chat before.
Okay, cool. I think I'll just go ahead and there's probably going to be some issues here. We're going to use Facebook's profit model. Facebook's profit model is another general additive model. I just see that it has really good performance metrics. In the past, I've used it instead of using ARIMA. You just call it the NAPI. Also, it's what Starbucks uses for their demand planning. So I think if companies along that scale are getting that sort of performance, it's good enough for me. One other funny thing is AWS, I believe, also uses a similar model in their AWS Forecast Service. So. Can you guys still see?
I can hear you. It might just be me because unfortunately my internet, courtesy of my internet provider Wave, is not always awesome. You're a little bit difficult to hear.
Okay. My internet also not always awesome. Turns out that Comcast wasn't really ready for the whole work from home initiative. So.
Yeah.
All right. So yeah, if everyone could just see if you can get this package downloaded.
ないですから。
Okay, so now if you want to, you should be able to re-pull or re-clone from Git. All of the updates should be pushed there now. So just go ahead and we're going to do the same thing that we just did. I've just re-split my train and test. I didn't have to, it was just to show you here. And also to have the code a little bit closer if we decided to do it on something else. And then also call the profit model, the API, fit to your data set, and then make a prediction for the next year. And I also want to know what my errors are and in a 95% confidence interval where my range is, not errors, excuse me. And then I'm going to go ahead and plot that out. And I think that this is way more in line with what we would expect to see over the next year here as compared to what we saw previously, where everything just sort of fell out between that flat 38, 39 incidents per day. And then if we wanted to try around 3 years as well. So now we have sort of two things that we can do. If you're working in a business and they say, we don't give a crap how you get it, just give us the number, we just want the number, you can stay with a univariate forecast. I don't know about your experience, most of the time mine is more of a, they want an explanation, not a number. And that's where they're hoping that something other than the traditional time series modeling can come in. So this is frustrating because you're always in sort of that trade-off between, do you want a good model that has good interpretation and interpretability, or do you want the more correct answer? And they're always like, yes. So I try to stick with, and I think mine's also because I'm just in a backwards industry. Like I work in the rental equipment industry. I try to stick with what gives the most accurate prediction, because business decisions are being made off of the prediction, not the gut feel behind the prediction. But if you wanted to, as a next step, you could get into multivariate, and we weren't able to cover that in this notebook. With multivariate, one of the things that you have to be cautious of is a lot of times you can't predict more than n+1 periods forward. So I've found, it depends on the algorithm that you use though, but I've found that the profit model is usually almost, it's able to create a prediction quickly, and you don't run into a lot of the same errors that you do when you're using Auto or REMA, and they're both sort of like general additive models. Excuse me. So one of the other cool things that you can do with profit is put in inflection points. So like I said, I work in the rental equipment industry. We have 2 conferences year over year that boost our sales. And if I wanted to predict sales, I could put in those 2 inflection points. Like, so if you worked in e-commerce, for example, you would put in the holiday season as an inflection point. So there's way more, I think, usefulness to the profit model than as compared to AutoArima. But so far, we've only done the original data set here. So if we wanted to, and I think maybe as a good practice for everyone, we could go back and see how our results are going to change if we take the original data set and change it to predicting this lagged data set. So everything that we had done originally was on a train and test of just our original data set here. I think changing that to predict on the lagged data set would be a good exercise, or be comfortable maybe taking 5-10 minutes and doing that. Okay, silence is agreement, so get started.
Can you take questions now, Victoria? Does anybody has any questions?
Oh, for sure, yeah. You guys don't want to just hear me breathe. You listen to me breathe too, that works. Okay, I think we can jump back in then. Okay. So I went ahead and I just changed, if we were to do the difference instead, take your differencing and go back through what does that look like. And when you take the differencing, as you can see, it sort of removes a lot of the that seasonal or cyclical components out of the data. What you would want to do here, though, is we haven't really talked about how you determine what is and what isn't a good forecast. And with the traditional techniques like your auto-ARIMA, using your profit model here, moving average model, any sort of smoothing, there's usually, you're going to look at your root mean square error or your mean square error or any sort of those, you know, back to basic statistics where you're taking some observed and expected value and comparing them. One of the things that is not considered with respect to when you're choosing the criteria that you want to optimize on is sort of like, are you okay being over or under your forecast? Like, what's easier for your business? So in manufacturing, for example, if you get rid of your labor force because of a bad forecast, saying you're not going to produce units, then it's much more difficult to sort of like rehire on the labor force as compared to if you you over forecast and maybe you have like just you're sitting on more inventory than was expected, but you can still burn through inventory. So it's one of those questions where you like need to go back to the business and understand what you're forecasting and which way do you want to reduce your error. Is it better to over forecast or is it better to under forecast? And every time, at least I've asked that question, I've been told, no, we want a spot on answer. To which I go back to like, we are just trying to clear up a crystal ball here. What is easier for you as a business or for the group? What's the better pattern here that you're trying to predict for? Okay. Are there any more questions? I think that this was all of the material that we had prepared, that I had prepared for today.
Maybe you can talk about what the ultimate bottom line information that we learned was when we tried to reduce the seasonality information. Do you think that will help us do a better job predicting future collisions?
Yeah, so when you do any of the the differencing methods, and if you were to compare that to a non-differenced data set, you're going to have a smaller mean square error. All of your performance metrics are going to be smaller. That's because it's apples to oranges. I think that what we learned here today, the biggest ones is how to spot autocorrelation, how to determine if you want to difference your data, knowing that you're violating the central theorem to autoarima, which is you need to have stationary data and how difficult it is to sort of transform into stationary data. I think that those were probably the biggest pieces that I hit on, and then also what your target variable is and how to choose the granularity that you want to predict at. If you want to predict on weekly basis or monthly basis, hourly, which you could have.
I forget exactly. I mean, we have a fair amount of data. We have a little over 220,000 rows. But with this amount of data, do you think that we could potentially go down to an hourly prediction level? Or do you think a daily prediction level is, with this data set, is the best we could potentially hope for?
Oh, I don't know. I didn't look at it. I think if you wanted to do it hourly, you could, right? So Uber, for example, if anybody is interested in forecasting, they have a lot of really great open source, not so much code, but so much as white papers and their methods, and how they developed their forecasts. And they do it down to, I think, down to the minute. I might be wrong there. Maybe it is to the hour. With really high accuracy, but a lot of that now is using sort of neural nets and deep learning.
Sure. Yeah, when I look at the summary data, the number of collisions per day, I mean, 30, 80, 21, 17, it varies. Good. If you don't have data for every hour.
I missed that.
Sorry, it just looks like my thing is frozen. Can you still hear me?
Yeah, I can still hear you.
Okay, awesome. So I'm not really sure that we necessarily do have enough in this little data set to do an hourly level prediction. I was just wondering what you thought.
I don't think for the use cases that we talked about, we probably forecast on an hourly basis. But I don't know off the top of my head. I didn't look at the how many data points do we usually have per day. I know that we were missing a lot of days, and I feel like I have a hard time believing that we go several days in a row without taking without.
Oh yeah,
but
definitely
probably
some
wrong.
questionable.
So, yeah. Yeah, I can share a requirements document so that we can see all the package versions we're using. For the minimum number of data points we need to reliably forecast, I think that depends on how many periods you're forecasting in the future. So like we saw earlier, it's not going to let you forecast more periods in the future than you have in your historical data. One of the like big things I did not touch on today that I should have touched on. When you get into multivariate forecasting, and this is one of the reasons I wanted to do multivariate forecasting, there's a big way that most people do cross-validation. You use some sort of like k-means cross-validation, something along those lines, right, where you're, or k-fold, excuse me, cross-validation, and you're randomly picking and choosing in your data set where you're validating. And that's like a huge data leak, like an information leak in a model test, because you are giving your model instances in the future and the past to predict on that future. So if you are going to move into any of the multivariate modeling and you want to understand the performance of your model, you should always use the time-based validation method, not the k-fold validation method. Sorry, that just like hit me. I know we haven't been doing it though. For people who are interested in joining in on the project, I think you should focus on a target variable that makes that's interesting to you. And also if there was maybe a different transformation that we could have done today that would have led to better results with AutoArima. And also if there was a point that AutoArima really failed. Like for us, it was always predicting between 38 and 39. If we had shortened our forecast window, like that's one of the questions I would want to answer. Like if we'd shortened our forecast window and maybe forecast just up to like March of 2019 or 2020, would have been able to better predict like the past few months. Yeah. For the multivariate type of forecasting, there are a lot more resources now. And I would also check out the AWS technical documentation for their forecast service, because it's a paid service that you're calling mostly open source models and Facebook profit model, and then there's a deep learning model that they also use there that's pretty easy to use.